rely on our factoring in order to be able to do some problems and to solve some equations. And before we do so, there's a very crucial theorem that I think we need to look at, and it's a theorem that you are familiar with, so let's state it anyhow. For every A and B belonging to the set of real numbers, A times B is equal to 0 if and only if and only if, what then you think our conclusion is? If and only if A is equal to 0, or, what may we say? B is equal to 0. Now notice, here is a theorem in which there are two parts to it. That is, if C is equal to, that is, if C, then D, let me just use those letters to interpret this, and also if D, then C. Is that right? In other words, we have two parts to this theorem that we must prove. There are two cases. Let's actually run through the proof of this, and I'll show you exactly what we mean. Here is our statement and the reason for that statement. Now, let's start out with case 1, in which we would like to say if A is equal to 0 or B is equal to 0, then A times B is equal to 0. Actually, the proof of this comes right out of the one of our basic properties, one of our axioms. And let's start out with our assumption, A is equal to 0 or B is equal to 0, in which this, the reason for this, of course, is what? Simply, Doug? Hypothesis. This is what's given to us. And in one step, I think we can conclude that therefore A times B is equal to 0. And our reason for saying this is what? And Doug?
Multiplicative axiom of 0.
There we have our multiplicative axiom of 0. So this first case is already done for us. And let's look then at the second case, namely the one in which if A times B is equal to 0, then A is 0 or B is 0. All right, this is what we'd like to prove. Now, let's see now, how may we start this? And let's start out with saying, well, we have A times B is equal to 0, and our reason for this again is simply what? Well, this is our hypothesis. Now, if it turns out, if, say, B is equal to 0, then the theorem is proved. Is that right? Then the theorem is proved. In other words, we're done. Because we want to prove then A is 0 or B is 0. So if it turns out that B is equal to 0, there's nothing more to prove. Is that right? So let's then say that if B is not 0, then we must prove what? What then must we prove? If it turns out that B is not equal to 0, Michael,
A is 0.
then we must prove that A is equal to 0. Okay? So let's then make that assumption that B is not 0, and let's just indicate that as an assumption. And let's then go back to A times B is equal to 0 in our step 1, okay? And let's then multiply both sides of this equality by what number? What number do you think we would like to look at? And anyone see where the direction which we'd like to go, Dick?
1 over B.
1 over B then is going to be equal to 0 times 1 over B. Is that right? And our reason for this is going to be what? What are we doing then from our assumption here that A times B is equal to 0? We then are multiplying both sides of this through by 1 over B. And Doug?
The multiplicative properties equality.
This is our multiplicative axiom of equality that enables us to do so. Let's continue the proof over here, in which then in step 4, on the left-hand side, well, let me simply repeat what we have. A times B times 1 over B then is 0 times 1 over B is what we have just stated. And now looking at this, what then may we say on the left-hand side? We may use what, Don? A times, well, let's put in that extra step if we can, if we may. And looking at this, let's just rewrite it in terms of B times 1 over B is equal to, let's just keep this as 0 times 1 over B. And what then enables us to go from this step to this step? And this is our property of what? What do we say then, Michael?
Associative.
This is our associative axiom with respect to multiplication. Is that right? Okay. And then in our next step there, Dawn, you say A times 1 is equal to, in fact, let's include two steps here, two reasons. 0 times 1 over B, of course, is what? 0. And here on the left-hand side, what reason enables us to say that B times 1 over B is 1? That's our,
Multiplicative inverse.
That's our multiplicative inverse axiom. multiplicative inverse axiom, and then of course 0 times 1 over b is 0. Our reason for that is our what? Our Malcolm? Multiplicative property or axiom of the number 0. And now of course a times 1 is equal to a is equal to 0, and in fact that's exactly what we wanted to prove. This is our what? Our multiplicative axiom of the number 1 enables us to say that a times 1 is a, and we conclude therefore that a is equal to 0. Are we done? Have we proved this theorem? Do you all agree that we have? Alright, notice again, let's come back here and make sure that we understand exactly what's what, in which if we have this phrase, when we have this phrase if and only if, remember that there are two parts to that theorem which must be proved. If C then D, and if D then C. And you must prove both parts of it in order to have a complete proof. Alright? Well, let's rely on this theorem in order to help us do some equations and solve some equations. For example, suppose we had a very simple little equation such as x minus 3 times x plus 4 is equal to 0. And here we have if a times b is equal to 0, therefore what is our conclusion? What can we write here in our next step? Therefore, Kirby,
x minus 3 equals 0.
X minus 3 equals 0.
Or x plus 4 equals 0.
Or x plus 4 equals 0. And notice now we have it broken up into two linear equations, so to speak. Therefore, here we have what? X is equal to 3, or x is equal to negative 4. And now if we were to write our solution set, what elements would be in our solution set here, but what may we say, Glenn? 3 comma negative 4, and notice that we have the two elements in our solution set, okay? Because now both of these numbers will make this sentence true. Well, let's then look at another example in which suppose it were written in the pattern of, let's say x squared plus 5x minus 14 is equal to 0. And in this case now we have to rely on what we know about factoring, and you look at the left-hand side and you say to yourself, well, I think I can write this as a product of two factors is equal to 0, and Peter says
X plus 7
x plus 7
times x minus 2.
times an x minus 2, because 7x minus 2x is plus 5x, and 7 times a negative 2 is a negative 14. And in fact, therefore, let's go right to our final step. X then is equal to, and Glenn? Negative 7, or
X is equal to 2.
x then is equal to 2, and then our solution set is going to consist of what elements here, Don? Negative 7 comma 2, and we have two numbers in our solution set which will solve this original equation. Is that right? Let's look at another example of one of these equations. And in this case, suppose we had 3 times x times. And now let's write this as x squared minus 6x plus 9 is equal to 0. And notice, in fact, if we were to multiply 3x times this, we would have a 3x cubed. We would have a cubic equation. But let's then think of it in terms of what we have here. And you look at that and you say to yourself, I think I may factor this. Let me write it first of all in terms of the product of two factors. And looking at x squared minus 6x plus 9 is one of our patterns. And Tim?
X minus 3
X minus 3
times x minus 3.
times another x minus 3. And we recognize that and say to ourselves, I think we can write this as x minus 3, the quantity squared. Well, let's leave it as this. And notice now we may use our theorem. We may extend our theorem that we just proved in terms of if a times b times c is equal to 0, then at least one of them must be 0. In other words, this number must be equal to 0, or this number must be equal to 0, or this number must be equal to 0. And therefore, let's then go right to our final conclusion. What sentences, what linear expressions or sentences, Rick, here may we write?
X equals 0.
Therefore, x equals 0,
X equals 3.
or x equals 3. And in fact, let's emphasize the fact that we may also say, or, what may we say again here from this statement, from this factor?
X equals 3.
Or x is equal to 3. And notice now, when we write our solution set, we simply want to indicate the two elements of 0, comma 3. And what we have here, with these two roots, if I may use that word, we have what we call a double root, all right? A double root, or we may speak in terms of roots of multiplicity, and in this case we will have multiplicity 2, because we have two that are the same. If we happen to have, say, x minus 3 to the 4th power, we then would have what? roots of multiplicity 4 in that case. And I think that it's worth pointing this kind of distinction out. Later on, in fact, we're going to have a theorem which is going to rely on this fact, the fact that we do have multiple roots in our equation, okay, in our solution set of the equation. Well, let's then look at a problem in which we have to interpret some sentences here, in which it says one of the perpendicular sides of a right triangle is 14 inches larger than the other. If the hypotenuse is 26 inches long, find the length of the other two sides. So let's make a little picture for ourselves here of a right triangle. And let's say that this is our right triangle. And one of the perpendicular sides is 14 inches longer than the other. So let's decide to call this one over here what? If we call this one x, the other one which is perpendicular to it must be what? X plus 14. And now the third side of the hypotenuse must be equal to what? 26. And simply, without stating what our variable is, except in terms of our picture, who would like to write an equation here? And what do we know about a right triangle? And Steve?
X squared
X squared
plus x plus 14 squared
plus x plus 14, the quantity squared,
equals 26 squared.
is equal to 26 squared. And of course, this comes right out of what statement? What do we know, Doug? What we call the Pythagorean theorem, which I'm sure you're all familiar with. Okay? Well, let's now solve this equation. And when we do so, notice here we have x squared plus. And now we have x plus 14, the quantity squared, which when multiplied out is what? So we have what? X squared plus 28x plus, and now what is 14 squared? Can anyone think of that number? Well, let's write it over here. 14 times 14 is what? That's 56, is that right? And 14 gives us what number?
196.
Is my arithmetic right? Please
Yeah.
check it. Is equal to plus 196. And then finally on the right-hand side we have 26 squared. And what then is 26 squared? Well, we have what? 36 and 156, is that right? And 12, and there's what? 52, is that right? So we have here what number? 676. So on the right-hand side we have 676. Now let's simplify this equation. We have here 2x squared plus 28x, and now let's subtract 196 from 676. Is that right? If we were to subtract 196 here, what then do we have? But what number? 480. Now let's subtract that number 480 from both sides, and on the right-hand side we have it equal to 0. And you look at this and you say, well, I think I can divide both sides by what number?
2.
By 2, and that gives us x squared plus what? 14x minus 240 is equal to 0. And you look at it and you hope that you may factor. Now on two numbers whose product is negative 240 and whose sum is positive 14, and what then are those numbers? Can anyone pull those out of his hat? Well, let's see. X times x is x squared.
X plus 24.
X plus 24, Peter says,
X minus 10.
times an x minus 10. In fact, the numbers are quite straightforward because we have there, what, 24x minus 10x is plus 14x and a negative 240. Therefore, x is equal to a negative 24, or x is equal to 10. Now, with respect to this equation that we have written right here, certainly x can be equal to a negative 24. But in terms of the original data of the problem, we are looking for that number which is the side of a triangle measured in so many inches. And how then, what can we do with the number negative 24? Let's simply indicate that it does not apply with respect to the data. So let's simply then discard it and say that that our solution then would be equal to what? Our number must be of length 10. Perhaps we should check. And the Pythagorean theorem tells us that that number squared plus the other side, which is what number? 24 squared is equal to what? 26 squared. And in fact, if you were to divide, first of all, if the sides are 10, 24, and 26, if you were to divide those by 2, you end up with what numbers? 5, 12, and 13. And you might recall those as what? Pythagorean triplets. But perhaps we had better check. And 10 squared is what? 100 plus 24 squared. We haven't yet calculated that number. 24 times 24 is what? 1696, 848, is this right? Check my arithmetic, please. That's what, 576? Is that checked? Plus 576 is equal to, and of course we've already calculated 26 squared, which is what number? Right here, 676, and I think you will agree that it checks. Therefore, what is our conclusion? The question asks, find the length of the other two sides. So answering that question, we have what? The lengths are 10 inches and what? 24 inches. Okay, well, I think that's all that we need to do for today. Let me give you your homework assignment. This will be